The purpose of this lecture is to discuss linear approximation. So what do we do here? We have seen already how to find the tangent to the graph of a function at a given point. And we have said that it's the line that approximates our function in the best possible way around that point. So, of course, assuming that our function is differentiable. And we only study differentiable functions in this course. So imagine that you have the point A. And now the idea is the following, that if you restrict your attention very, very close to the point A, then there's not much difference between the points that lie on the tangent and the points on the graph. What do I mean by this? It might be useful to actually magnify this a little. So this is your function, and this is the graph of the, this is the tangent, meaning the graph of the, of another function that, let's see what that function would be. So we know that the equation of the tangent is this. And if we want to view the tangent itself as a graph, then we have to solve for y. And we find this function, which is actually a linear function. After all, remember that both f of a and f prime of a and a are known numbers, known quantities. So if we define the function g of x as f of a plus f prime of a times x minus a, then this is a function whose graph I should say the function whose graph is the tangent line at a comma f of a. So the approach that we're going to explore today is that for the principle that we're going to explore is that for x close to a, so I will denote it like this, for x close to a, g of x is close to f of x. Okay, and you can see it in this magnification or supposed magnification that I drew, that if I take a point on the graph of the function, then the corresponding point on the tangent line is very close. Of course, you have to be pretty close to A, to the center of the whole situation, meaning the point at which the tangent was sketched. And you're getting pretty much that the outputs of the function and its approximation, which is going to be called the linear approximation of f of x centered at a. Okay, and this is what we're going to see today. Now, one point that I should stretch here is the fact, one point that I should emphasize here is the fact that different functions are going to have different degrees of approximation around that point. So if you have a function that has, how should I put it, more curvy graph, then there is a chance that you will have to restrict closer to the point under equation in order to achieve good approximations. There are ways to quantify how good the approximation is, but we're really not going to look into them. And in fact, for today at least, we're going to look at some pretty rough approximation. So let's start with a typical example. So estimate square root of 10 as a fraction AB with natural numbers A comma B. Okay, I mean, this is kind of very vague, but I would like to just do it in the context of linear approximation. So I could say estimate square root of 10 by using an appropriate linear approximation. Even in that case, one could actually consider different things, but here's the basic approach that we would like to take. So first of all, let's agree that finding square root of 10 is not the most straightforward thing in the world. It's not that hard either, but it's not a finite, it doesn't have a finite decimal expansion. So it's an irrational number. It has infinitely many decimals that do not have any repetition pattern. There are repetition patterns for square root of 2 in other representations as continued fractions, but not like this. And we would like to just find a nice fraction that could be a rough guess to what square root of 10 is. So the idea is to consider the function square root of x as a whole function and ask, is there any number close to square root of 10 where, close to 10, where computation of a square root is straightforward? And the answer is, of course, you have 9. I mean, some people might say you have 9 and then you have 16. Square root of 9 is 3, square root of 16 is 4, but the closer is 9. So we will use a linear approximation. And I should say here, the linear approximation. It's not like there are many in the context that we gave. The linear approximation of f of x, we have to define what function we're talking about, square root of x, centered at a equals 9. So what is f of 9? It's 3. What is the derivative of f of x? F of x derivative is 1 over 2 square root of x, and f prime at 9 is equal to 1 over 2 times square root of 9, which is 1/6. So the linear approximation is g of x is equal to f of 9 plus f prime of 9 times x minus 9, which is the same thing as 3 plus 1/6 times x minus 9. So f of 10 is going to be approximately equal to g of 10. And g of 10 is how much? So it's 3 plus 1/6 times 10 minus 9, which is 3 plus 1/6. and that's 18 over 6. That's what 3 is, plus 1/6. That's 19 over 6. So our final answer is that square root of 10 is approximately equal to 19 over 6. Okay, and there's certainly more ways to explore these patterns, and there's actually a very interesting concept here, which is did the number that we get is the number that we got an overestimate or an underestimate? Meaning, is it larger than the actual square root or smaller than the actual square root? To understand what the answer is, we have to know what the function square root of x looks like. And the function square root of x looks like this. It's concave. Oops. What I wanted to say is that it's concave down. And this means that if at a given point you sketch the tangent, then the tangent is over the graph, which means that all estimates that you're going to find if you use a linear approximation are going to be overestimates. We were not asked to find this, but it's a good point to make. So if you find the second derivative at 9, and if you find the second derivative at 9, you will see that it's less than 0, which means that the function is concave up, and the linear approximation is will always produce overestimates. I'm sorry, I said concave down, and the linear approximation will produce overestimates. If it was concave up, then the linear approximation would give underestimates. As I said, none of these things were necessary in this exercise, but we mentioned this as a further discussion on what we just did. And let's do one more example. We're going to just limit ourselves to these very simple examples of computing or of estimating roots. So as a second example, estimate the fifth root of 30 by using an appropriate linear approximation. And express your answer. In the form A over B, where A and B are natural numbers. Okay, so as a solution, we will do pretty much the same thing. So we define f of x to be the fifth root of x, and choose a equals, okay, so what do we want the center of approximation to be? We want a number that has a nice fifth root, which is close to 30. Okay, so can you think of a number that is a fifth power and is close to 30? I hope you all answered 32. So 32 is a fifth power, so we will choose this as the center of our approximation. Well, what is f of 32? F of 32 is the fifth root of 32, which is 2. And f prime of x will be, so this is x to the 1/5. Let's write it as x to the 1/5. So it's the derivative of x to the 1/5. And this is 1/5 x to the negative 4/5. Okay, and now we need to know what f prime specifically at 32 is. And this is going to be 1/5, 32 to the negative 4/5. which is 1/5. What do we do here? We can take 32 and raise it first to the 1/5 and then to the -4. And 32 to the 1/5 is 2, because it's a 5th root of 32. And then 2 to the -4 is 1/2 to the 4th, which is 1/16. And this gives you 1/80. Okay, so we have everything that we need. What is the linear approximation? The linear approximation is going to be f of 32 plus f prime at 32 times x minus 32. And this is equal to 2 plus 1/80 times x minus 32. And finally, f, so the square root of 30, which is f of 30, is approximately equal to g of 30. And how much is g of 30? 2 plus 1/80 times 30 minus 32, which is 2 plus 1/80 times -2, which is 2 minus 1/40. And 2 is the same thing as 80/40 minus 1/40. So that's 79/40. Okay. And that's it. So our guesstimate, if you like, for the square root of 30 is that it's 79/40. If we did an analysis similar to what we did before, then we would find that this function has also a concave down graph, and it's also concave down, and this is going to be again an overestimate. So with these two very similar to each other examples, we finish our account of linear approximation. Thanks for watching.